So I am very grateful to the organizers for the opportunity to be here and to give this talk. The talk will be about some optimal transport-like problems which are valued in matrix-valued measures. It's not exactly quantum, but still valued in non-negative definite matrix-valued measures. So, but let me start with some which seems to be unrelated, but it's important to understand what is being done in this area. So this is a very simple notion. I am not claiming any novelty here. So, but just to fix the ideas. So if you have a manifold, a Riemannian manifold, and you have a vector field on it, and then you fix one point on the manifold, which is xt, which will be your final point. So by ballistic, so this name is probably there exist other names. This is just some name which some people use to call this kind of problem. So ballistic problem means that you look for a geodesic, but you don't know the initial point of the geodesic, but just the initial velocity. And you know the final point, but you don't know the initial point. You know the initial velocity, and because you cannot fix one velocity on a manifold, you need a vector field to fix one velocity at every point. That's why it's called ballistic. So you have something like a howitzer, a cannon at every point with fixed direction, but you should select the one which will hit the target, optimizing the energy. And so if your vector field is a gradient of something, then you can write this problem in a neat way, at least formally, where this is a geodesic distance on the manifold, and then there is extra term. So this is like Hopf-Flachs formula, which you use to solve the Hamilton-Jacobi equation. But here you are not interested in solving the Hamilton-Jacobi equation. You are only interested in optimizing x0, so finding the initial point. You're not interested in the value of this. You're only interested in the optimizer. And but what's good in this is that this formula has nothing to do with manifolds, right? It just can write it on any metric space. And in particular, it appears in optimal transport in the Georgi scheme and other contexts, and was studied by Ambrosio and people like him in some contexts, independently also on the GKO scheme.
Can I ask a question?
Yeah.
In the first page, you fix the vector field, right?
Yes. And now
Where is it in
still
number
fixing
one?
it, but now I assume that this vector field is a gradient.
Yeah, but even in number one, you don't mention the vector field at all. So I was wondering.
It is the starting condition.
It is.
Oh, it's just the starting condition.
Yeah, the vector field is just you know the velocity at every point, right? But you need to select the point to start from it. Oh, you can invert and if you formulate it in the spirit of Millfield games, then you are reaching. But for me, it's convenient to call it as an initial moment and the final position you know. But if you swap, then yes, it's like Millfield games in some sense. So it's really not something very advanced. It's just you look for a geodesic with you know the target and you know the initial velocity, but you don't know the initial position. So this is like essentially this is like Neumann mixed boundary condition, right? So you have Neumann the inhomogeneous Neumann at 0 and directly at 1.
So silly question, sorry, but like you're not looking for a geodesic, right? Because if you
I look.
If I have 2 points, initial point and final point, and I have a unique geodesic, and then I ballistically shoot in the wrong direction, then I will never get a geodesic, right?
Yeah.
So it's not really a geodesic in the sense of Riemannian geodesic. It's more like a minimizer of the problem.
Yeah, it's a minimizer of the problem.
Yeah.
No, but it will be a geodesic a posteriori if you know when you find well, at least if you have a geodesic space and everything is fine, then if you find this unknown x0, then a posteriori it will be a geodesic.
Only if the velocity at the beginning was the right one.
Sorry?
Maybe I'm wrong, so it's fine.
No, I think it's still fine.
Because if you have 2 points and I have a unique geodesic connecting them, which can happen,
Yeah.
there is a unique velocity I can choose to choose that geodesic. If I choose a different velocity,
No, but you don't know the point. You are adapting the point in such a way that it will hit.
Also, the initial point is adapted.
The initial point is unknown. The initial point is unknown, and you are choosing the point from which you will hit it. So if you cannot hit this point, this is just not eligible, and you don't care. But so I'm not speaking if this is solvable or not. Just to fix the ideas. So also these kind of problems, they appear in infinite dimensional context. Essentially, I'm interested in this more than in the first page, right? So and this is quite a classical object. This is essentially what you have in the GQO scheme. And also in Liro, Milky, Savary, these kind of problems are called marginal entropy transport, but typically in their setting, this functional would be something like superlinear. And for us, typically like linear functional. And also, it's somehow similar to Milky games if you swap the initial and final points. So let me show you how these kind of problems appear in the Wasserstein space when you, in a natural way. When you start from just any PDE, you start essentially from Hamilton-Jacobi PDE first, and how it generates you this kind of problem. So you start from the Hamilton-Jacobi PDE, quadratic one, and you fix the initial condition. And then you can just change the variable, denote the gradient of the solution by V, and then you write it in this style. So this is like Berger's equation, but multidimensional. And then let's consider the problem of finding the weak solution, which would minimize the kinetic energy. So formally, the kinetic energy is conserved. But because of shocks, it can actually, for weak solutions, it can be not conserved. So this problem makes sense. You are not sure whether so if you only consider smooth solutions, then this problem is nonsense. Just you're not minimizing anything because you're minimizing a constant. But if you consider weak solutions, then this is valuable. This makes sense. You look for the weak solution which optimizes this Lagrangian action. And again, I'm not interested now whether this has a solution or not. I'm interested in the duality. So this problem has a dual problem, and the dual problem looks quite nicely. So look, this term, look that this is like a Benamou-Brenier formulation of optimal transport. This is also like Benamou-Brenier, and you have some extra term. So if you define this functional, linear functional actually, on the Wasserstein space, multiply this by -1 to get rid of the minus, and sup becomes minimum, and then what you get is exactly, because this Benamou-Brenier term gives you the Wasserstein distance, and you get a Hopf-Flachs formula. So you get a ballistic problem. So this is what I call ballistic optimal transport in some sense. Then, so in 1D it's even simpler. It's just the Berger's equation, which is a conservation law. But Brenier particularly studied the one-dimensional situation and showed that entropy solutions of the Berger's equation, they can be somehow, the information about them is contained in this dual problem in some sense, whatever it should be. Now you can play this game with other PDEs. So in particular, a good example is the Euler equation. So again, you take the Euler equation, the kinetic energy is formally conserved, but for weak solutions, it's not guaranteed. So again, you look for the solution, for the weak solution, which would minimize the total Lagrangian action, the integral of the kinetic energy. And this is not nonsense, because if the solutions are not smooth, they are not obliged to conserve the energy. And so you can also write the dual problem. So the dual problem looks like this. So look, that this is similar to Benamou-Brenier, but now G is the matrix value density. So G is matrix value density, so the transport equation now looks like this, where P is of course, you have to have some Leray projection because you are studying fluid dynamics now. So P is the projection to divergence-free fields. And well, this is formal, but can be made rigorous. This is formal, but can be made rigorous. And the final, the final density is just the identity matrix. But the initial, you don't know, because this is like ballistic. But you have this term on the left, which is exactly as is in the ballistic style problem. So this is like matrix valued transport in some sense with this generalized transport relation and with matrix valued densities. And also you have this term which comes from, comes from the initial datum. So in some sense, this is your initial, this generates this velocity field on the manifold, and there is no manifold now, right? This is something, some strange metric space which probably does not exist even, related to this optimal transport, which we don't care what it is, but still you have a ballistic problem, in spite of not even explicitly being identified. I'm not identifying the metric space on which it actually is set. But still, it's clear that it is ballistic problem because it's very similar to what was for burgers. And so what are some interim conclusions? So these kind of problems, they can emerge from dual formulation of Cauchy problems for PDEs. If you go beyond the quadratic Hamilton-Jacobi case, you typically get a matrix-valued transport, transport, not exactly transport, but something similar to transport. And these problems are expected to, you can believe that these dual problems, they have some information about the physically relevant solution, because typically the solution is not unique, weak solution is not unique. And the question of how to select the physically relevant one is an important question. And you can expect that because it's duality, so something reasonable, so you can expect that at least for burgers, entropy solutions can be recovered. So you can believe that it can also indicate you some way to find a good solution, a good weak solution when they are not unique for any other PDEs. So there has been work done in this direction. So, for example, Brenier and Moyano, they studied the Euler-Poisson system in this with these ideas. I also studied, developed some systematic approach, quite abstract, which allows to study many quadratic PDEs and prove some results. So you can prove existence of the dual problem, prove some consistency, prove some weak strong uniqueness, absence of duality gap, and so it's convenient to do it in a quite abstract way because then you can simultaneously include many equations in the theory. And also there is a recent preprint by Mirabeau and Stamfli, which study this ballistic formulation of the porous medium and of burgers, but numerically and also convergence of the numerical scheme. And there is also another group from Carnegie Mellon, essentially, which rather independently develop similar kind of ideas, but with there is some difference because in their construction they also have some kind of base state, which in Brenier case is just 0, and this base state helps to get some kind of consistency. So this base state can be viewed as kind of initial guess for the solution of the PDE that you want to solve. So I don't describe this in detail because this would require some extra time. But some people, many people actually, there is a quite big, there are like 10 or 15 preprints on this from this group, very recently. So now I already mentioned that this is related, might be related, hopefully, to some selection principles for weak solutions. So let me discuss briefly the selection principles because I will need it, because essentially I will show you how this kind of theory is related to so-called Dafermos principle. So the general remark is that problems which are difficult can have many weak solutions for fixed initial datum. And this is in particular observed in a systematic way in convex integration. And there is no essentially universal selection principle. At least there are some particular selection principles. The universal idea does not exist. But what can be observed? That some problems of this kind, they have formally conserved quantity, which you can call entropy or energy, depending on the context. I will call it entropy, because I'm inspired somehow by conservation laws. In conservation laws, entropy is something which is formally conserved. But of course, for heat equation, entropy is something different. But here I'm mostly interested in like hyperbolic-like equations, which like Euler as well, or Burger's, or any other examples, they are more hyperbolic than parabolic, and so they still it's convenient to call this entropy. I prefer this is just a voluntarist choice, because in the theory of conservation laws it is called entropy. So some object which is formally conserved, but is not conserved for weak solutions because shocks destroy it. Let me also briefly remark that there are some principles in natural sciences which might help you to select the correct weak solutions. For example, there is Prigozhin principle, also Ziegler principle, and many other principles in many areas of science. But, so these principles can be used. Typically, they are used for derivation of PDEs, but they can also be used for selection of the, if you have non-uniqueness of weak solutions, you can try to use this principle for selection of the relevant solution. In particular, more mathematical flavor is so-called Dafermos principle, which is somehow similar to Ziegler principle. So you select the solution which dissipates the total entropy earlier and faster than the other solutions. Earlier, what does it mean earlier? That typically, first you have a smooth solution, and then, sorry, I will use the blackboard just for one moment. So typically what happens, you have a smooth solution at the beginning, just probably unique. And then you have some bifurcation. So the correct solution, which Dafermos suggests, would minimize, so this is the energy, the entropy, and this is time. So the correct solution would dissipate the entropy faster than the others. But what is local? So it is even not prohibited, this is weird, but still it's allowed to go like this. Also you can go like this, it doesn't matter. But what matters that locally, where near the bifurcation time, somehow, the optimal solution, the best solution should dissipate the entropy faster than the others. This is the Dafermos principle, and this is in particular for some conservation laws. This is really selects the entropy solutions, etc. And also for some other equations like Hunter-Saxton, etc. This really gives you the correct solution. So you can check that this principle works. And so there are many works. It's quite old, right? It's 73, and there are some works which checked this for different models. And there are also recent numerical applications of this principle by Klein, many papers by Klein. Of course, there are other principles. For example, for conservation laws, there are like other selection principles due to Khrushchev, Lux, Liu, and others. And the Dafermos principle typically complies with that. Also, the Dafermos principle, you should not restrict only to conservation laws. This is a generic. You can use it for any system of PDEs. Yes, and so let me go back to this duality scheme now. So it was clear from the very beginning that nonlinearity does not need to be quadratic. Of course, quadratic is more Wasserstein style. But in principle, the scheme works not only for quadratic nonlinearities, but it's easier to obtain rigorous results if you want to do mathematics for quadratic nonlinearities. But of course, many systems are not quadratic. In particular, systems of conservation laws are not quadratic, generally speaking, if it's not Burger's. And also, I have another class of examples which I'm interested in, like this nonlinear Schrödinger equation or something similar, like nonlinear Korteweg-de Vries, etc. So they all have some similar nature, So I'm interested in this kind of equations. So of course, this function f can be anything, but typically it's a power law. But even for power law, even if f is just identity, this is not quadratic. Another representative example is this motion of barotropic fluids. You also see that the corresponding energy here is not a quadratic thing. So I want to do it again in quite systematic way. So I want just to study this in abstract way. So I consider any PDE which can be written in this form, where L is just a linear differential operator, which can include also zero-order terms. And F is some matrix of some dimension, which depends on the solution. So you have a system, n-dimensional unknown V, and you have some matrix which is auxiliary in order to write my PDE in this way, and then you can check that many PDEs actually fit into this framework. So in quadratic case, let me anticipate. In the quadratic case, this f of v is just v times v. It's a matrix, of course, right? And a good matrix. It's a positive definite and convex in some matrix valued sense. But and so I want still some convexity and positivity properties for this matrix, but very weak ones. So not in some weak sense, some relaxed sense, in order to be able to do the scheme, and not only to do the scheme, but to prove something about it. So then now there is this problem comes with some natural, probably, let me write down the problem here in order to have it indefinitely. So L is a linear differential operator, F is some matrix which depends on the solution.
So do you have a minimum rate derivation, high level derivation that you impose to have, or you can have also just zero terms?
Yeah, any zero terms are also involved,
but also can also be only zero, so you don't need to have.
Yeah, it can, but typically if you have only zero terms, it's like an ODE,
yeah, exactly.
And typically would not conserve. It typically does not have conserved quantities.
Right, that's why I'm asking. So it has to be a very large class.
So you assume that there is some entropy. The entropy is just a trace, essentially, of this matrix. So in many examples, you can check that. There are some assumptions. And the main assumption is this: you have this entropy, which is essentially the trace, which you subtract the initial value because you want this entropy to be 0 at 0. And yeah, assume that this entropy is strictly convex. So the trace of this matrix is essentially strictly convex, but not uniformly, right? Because you want to include power laws. So it's strictly convex, but not uniformly convex. Because you essentially you need here so-called anisotropic Orley spaces in order to work with this. Because anisotropic Orley space is something, is a space of functions for which this is integrable, right? And this K is typically anisotropic. So this K is typically anisotropic, as you will see. Of course, in the quadratic case, it's isotropic. It's just the power, V squared, right? So the trace of this in the quadratic case is just V squared, and it's isotropic. But in other examples, like in particular this examples like nonlinear Schrödinger, you get anisotropic energy. And that's why you need anisotropic Orley space to work with this.
Dmitry, I'm sorry, but so now I'm confused. You say that this entropy, in the first slice, you say this was at least formally conserved along the flow. I don't see how.
But now it's abstract. Look, I will say. Now I just this is abstract setting. So first I just write it in this way. Of course, this is too abstract. Now I need some assumptions. So the first assumption, I first just denote the trace minus some constant. I call it entropy. It's just abstract. Then. So I even didn't ask the entropy to be conserved yet, but I will ask later. And now, well, because we are in this non-quadratic case, we have some strange extra Legendre duality here. So if you have some V, which is your unknown of your PDE typically, it comes with some dual variable, which is a natural in this setting, which is just gradient. You take the gradient of the entropy and you apply it. You get some. So this is a kind of natural change of variables which appears here quite naturally. It's convenient to notice it. And in the case when the k is so. In the quadratic case, this is nothing, right? Because in the quadratic case, k is just 1/2 of v squared. And so the gradient is just v, and nothing changes. So v and v sharp is the same thing. But this is a specific thing which appears in the non-quadratic case that you need this kind of extra Legendre duality. And also I need some convexity assumption, but this I probably will skip because this is really a little bit messy, but I just want to say that this is a kind of relaxed kind of convexity. So this is weaker than the classical convexity for matrices. Because for nonlinear Schrödinger, I'm not able to check the classical convexity matrix value, which is called Löwner convexity. So what I will be assuming is something weaker than Löwner convexity. But it's a bit difficult to describe, and there is no time. And also there is also corresponding order, which is a weaker order than just comparing. So this is not necessarily positive definite. This is weaker. Include positive definite matrices, but a bigger set than positive definite matrices. And so, yes, this is quadratic, which is already said. And already quadratic includes many interesting examples, but I'm now interested also in not quadratic problems. And now we assume this conservativity. Conservativity essentially implies that the entropy, total entropy is conserved along the flow, formally. You can write it in this algebraic way. So typical example is this defocusing NLS, but you need to rewrite it in some weird way in order to fit into my framework. And then you see that the corresponding entropy is anisotropic. So you see that here you have different power. And then, so the corresponding F, you see, it's quite messy. but still, in order to fit into this scheme, you need some tricks.
Where's the Q coming from?
Sorry?
The Q? Where's the Q coming from?
Q is the power of the
nonlinear term.
yeah, this.
Okay.
Yeah.
Sorry.
Yeah. Well, it can be also done for other convex functions, but for simplicity, I consider here the power law. But in principle, it does not need to be a power necessarily. But for power, it's more neat. And then you see that the corresponding L is like this, and this is the dual, some space lambda, which is needed to define this relaxed convexity, involves this kind of matrices. And this is V sharp, looks like this. And then you can define weak solutions in quite natural way here just by some duality. I think I don't have much time, so I will. So this is a natural definition. There is nothing here, but natural but abstract works in the abstract setting. Then you can also define subsolutions, and then you can. So it's remarkable that you can rewrite your problem in the terms of this dual variable, which is V sharp, and it's still quite neat, quite short. And all my scheme is strongly relies on the fact that you can rewrite, at least formally, the problem in the dual way like this. Then you define some strong solutions, which are much stronger. And the strong solutions, in particular, they conserve the total entropy. But the weak solutions, they don't. And what's interesting that I'm here to prove that in this abstract formulation that the strong solutions conserve the entropy, I use the call. So I studied the evolution of this Jeffreys divergence. Why I call it Jeffreys divergence? Because if your entropy is U log U or Boltzmann, then what you get is the symmetrized Kullback-Leibniz, which is called Jeffreys. But of course, this is more abstract, right? So this coincides with symmetrized Kullback-Leibniz if you're for the particular entropy. And also this matrix valued and KL is just a scalar. And so there is some extra thing with the weights, which is kind of technical. And so, but what matters? So I put some weight for some reason, which I need in order to implement to get some conclusions for the Dafermos principle, in order to get link to the Dafermos principle. So typically, you are not minimizing. So this H can be just 1, then you minimize the action. But now I put some weight in the action, which depends on time. This is needed for in order to get some applications for the Dafermos principle. And then, so this is the saddle point problem. So I can formulate my problem in minimizing the entropy for weak solutions in this way, in the saddle point way. And then the dual problem is just you swap inf and sup. So you swap inf and sup, you get this dual problem. And well, in spite of looking differently from the ballistic problem, you can actually write it, at least formally, in a more ballistic way. And so this is the geometrical density here, actually unknown one. And here, this 12 is a weak form of the transport equation in some sense. But of course, abstract counterpart of it. So this is, in some sense, this still has links with matrix valued optimal transport, but in quite abstract way. And this is matricial and also non-negative definite, this one. And actually non-negative definite in classical sense, not in generalized sense. And so, and we can prove consistency. So consistency here means that if you have a strong solution, then it generates a solution of the dual problem. And there is quite neat link between this strong solution and the solution of the dual problem. And so in order to get this neat link, you need this conservativity. Actually, there are other ways to go from the dual problem to primal, but this is the most neat in my opinion, because the formula is really very short, even at this level of generality. So there is, by the way, there is some restriction here. How much time?
You have almost like 18 minutes or so.
So yeah, I'm confused. Sorry, I was so fast because I thought that I started at 10. Okay. So I don't need to be so. Sorry, really so fast because I thought that I'm out of time. Then I can probably return to some issues and discuss in more detail. Okay. So let me then discuss this theorem in more detail. So you take this weight, you take this the primitive of the weight, and you take a strong solution. And you put some restriction on your solution. But you will see that this restriction is actually not indeed a restriction. And then there is no duality gap. So then the primal and the dual problem have the same value. And moreover,
since you're not really in a time rush, right? Can you remind us a little bit? So this greater or equal is, in your theorem, is that the greater or equal in the matrix sense, or is the scalar?
This is greater than equal in the matrix sense, and in the just the difference is positive definite.
Okay. And h of t is a scalar or a matrix?
H is a scalar. But identity here, this is identity times some weight. And here you have primitive of the weight. So why I put the weights? Because if I put the weight like this, so if f of t is big, then the primitive is, and gamma is big, then the primitive is much smaller, right? And that's why it's easy to have this inequality, because the primitive of this function is much smaller than this function itself. And that's why I need this kind of weights. And so when you have this kind of weight with B gamma, this inequality holds, well, assuming that this is somehow bounded. You just you take your solution and sorry. No, but this is you take a solution which is a strong solution, so it has L star is just your but you assume that the solution is strong, so even L star of the solution is bounded. The strong solution means, if you see, that L star is bounded. L star is your differential operator, which you have in your so the adjoint of your differential operator, and you assume that that it is bounded, and this is the strong solution. How you define strong solution?
What you wrote down is some condition on the spectrum of L star of E sharp, right?
No, it's not the solution. I think he's saying you have a strong solution which is semi-concave in some sense.
Okay.
No, the strong solution is not concave. Anything.
Wow, that's what you're saying, right?
What?
It's the condition of the
next
solution.
page. In the next page.
In the next page where you put this H bar,
Right,
so
you
H
have an
identity
estimate
bigger or
of
equal
the-
than something, then that's what you're.
So if you
Yeah, 17 means that the solution.
17 means that so because look that
you can divide by h of little t, and then you just have a lower estimate on the eigenvalue.
no, but the point is that identity is something fixed, right? And this is the primitive. So if the time interval is small, if t is small first, then this always holds because this is small. This is you integrate with respect to small interval. But now I want to do it on big intervals. So that's the point of the weights. If you don't put the weight, if you h what Brenier did, if h is just 1, that this is the primitive just t minus t, and then this is small if t is small, and then you still have consistency on small time intervals. But now if you do these weights, then you can have this inequality even. So this does not matter. This is something bounded for strong solutions. So this is just very simple algebra. If your weight is like this, then you have this inequality for gamma sufficiently big.
It
So this is the
still
trick.
tells you something that the minimal eigenvalue of L star of E hat is not too large, I think. Right? You can do the minus on the other side, and then you're bounding your.
No, but if you do the what matters is the absolute value
We're
here.
discussing.
Anyway, okay, that doesn't matter. It's
Yeah,
very
you just
reasonable condition.
this is so what matters. The eigenvalues of this are bounded by the minimum of the eigenvalues of this is fixed eigenvalue. So it's not a matter of above or below. It's just quite rough.
Right, but it tells you that your process doesn't stop too early.
No, this is just algebra. This is nothing. Okay, let's continue. Okay, it's really not so important. So then you don't have duality gap, and moreover you can just explicitly write down the solution of the dual problem. So you take A, which you take this sharp variable, and then you take H, and then you plug it here, and this is the solution. This solves the dual problem. I'm not claiming here that this is the only solution of the dual problem, but this is a very plausible. In quadratic case, I can prove that this is the only solution of the dual problem. In the non-quadratic, I still didn't prove it, but it's plausible also that if you have a strong solution, that the only solution of the dual problem is this one, and so it's kind of weak-strong uniqueness. But here at this level, because of this Legendre and quite messy, so I still didn't prove that this is the only solution, but it's quite plausible. And moreover, you can go back, so you just invert these formulas, and when you invert in them, you get this quite neat relation. So if you solve the dual problem, and then you plug, so you calculate this, you get your original solution.
So the dual problem gives you some solution. now.
Yes, so this is the idea now. I will discuss it on next slides. That now, if you even if you don't have a strong solution, you can do the same formula and you get some object. Yes, so this is the trick. Yes, but probably it's not the best object. So let's I will talk about this. But first I discuss the fact that 17, yes, this restriction 17. It might looks restrictive, but actually, if you take the weight, which is yeah, like this, then everything is okay. So essentially, there is no restriction. And now this Dafermos principle. So the application of this is this Dafermos-like statement. So assume that you have strong solution which conserves the entropy, right? Because strong solutions, they conserve the entropy. And then you take a weak solution, which has some entropy, depending on type, which probably is not conserved, right? And then it cannot happen that this entropy is smaller than the entropy of the strong solution, and it becomes even, well, so if this is the strong solution, and this is the weak one. So it cannot happen like this, right? So the weak cannot have, so this is not allowed. Weak cannot have bigger entropy than the small one, right? So what is allowed, and I'm not saying that it's not allowed, is this, right? So what is allowed, so you have the strong one, this is the weak. Like this. This is allowed, and because in this setting, this is my T0 and this is my T1. So this is allowed. I cannot say that this is not true, but this is not allowed. So it at least near the point of the bifurcation, the strong solution has the no, it's other way around, right? Yeah, it's the other way around. So the strong solution has minimal, yeah, so this is allowed, right? So this is a weak, and this is strong. So the strong solution dissipates, well, it does not dissipate, but dissipates more than the others, right? So the others are obliged to grow, right? This is allowed, but, so this is the typical behavior. So this is exactly what the Dafermos principle tells you. And moreover, this is true even if you take a subsolution. So this is really surprising because I didn't see this before. That so you take even a subsolution here, and it's still the Dafermos principle selects the strong solution, even within subsolutions. So even subsolutions should only behave like this. They cannot go down. They cannot be better than the strong solutions. In particular, if your bifurcation appears at the beginning, right? So this is also possible, right? So it can, if the bifurcation appears at the beginning, and this is your strong solution, and the weak can be immediately bigger, right? So this is also possible. So this is strong, and this is weak. But we cannot be more optimal. So this is this Dafermos principle. It's new even in the quadratic case, and in particular, it's applicable to incompressible Euler. This group from Carnegie Mellon, they recently also obtained some, yeah, and also the consistency result is with these weights is somehow it's not is new for quadratic problems, even for quadratic problems. And let me remark also that this group for Carnegie Mellon, they not only for Carnegie Mellon, right? So this is from Italy and this is from elsewhere, and they recently obtained also some kind of consistency but their consistency is different. So in there, they have some extra thing in the scheme, which is called base state, and they prove consistency if this base state coincides with the solution. And then the dual problem is just has identically zero solution. So in this case, it's very easy to prove consistency. So in some sense, this is so their consistency does not is not full consistency. It's just a trick in some sense. And so this is more systematic because this really relies on conservativity and really relies on this formula which relates the primal and the dual problem. So and in their case, the dual problem is just identically zero. So of course the solution is optimal, and then in this case there is nothing to prove. And also we can prove that the dual problem has a solution actually. Yeah, because I still didn't speak about that. I left it to the last slide. So the dual problem has a solution under our assumptions. And this solution lies in the Orly space, which is, by the way, funny because you know that typically for optimal transport, well, with at least quite abstract optimal transport, the solution is a measure, right? The solution typically is not a bounded function or integrable density, right? The solution is just a measure. But here, because of conservativity, essentially, your solution is in the Orly space. So it's not a measure. The solution lies in this class. Yes, in this class. So it's bounded actually. B is what E is in some sense the flux, or not? E is the abstract flux, and B is the abstract density. Well, not B, but this is the abstract density. Let me. So this is the abstract density, and so this is this non-negative definite matrix valued density, but this is bounded. So for these ballistic problems, the solution is more regular than in the classical optimal transport, even at this level of generality. And the flux, look, so the flux is Orly space, a dual Orly space. The flux is in the dual Orly space, but the density is bounded. And yes, and then your idea, you can take this formula and define, you solve the dual problem, take this formula which worked for strong solutions, and define some object which you call a generalized solution for anything, for Euler, for nonlinear Schrödinger with any kind of nonlinearity, or other problems I considered, MHD, etc. And then it gives you some object, but this object is actually quite regular. So this is the problem. This object has no shocks. So in particular, if you take the Burger's equation, very simple example, then what you get is this what Brenier calls shock-free substitute for the entropy solution. So it's not the entropy solution itself, but some shock-free substitute for it. And also, so what does it mean? This means that this formula is neat, but still probably, but still there are other ways. So, for example, Brenier describes for Burger's equations how to get the, so the dual problem still has the information about the correct entropy solution, but maybe this is not the best way to get it. There are other ways, and still, so this is still ongoing, how to get the correct solution from the dual problem at the maximal level of generality. So this problem is very tempting to use it because this is quite neat. But what you get is typically some substitute of the solution, some shock-free substitute, some solution which is has a relation to your problem, but is somewhat quite regular, too regular, more regular than you need. But for example, what Brenier does for burgers is that, so you do this formula. Well, in his case, it's simpler because burgers is simpler than this. So you do this formula, you get some object, and at least at the final moment, it agrees with the entropy solution. So it has some link, still has some link. And also, as already said, we also expect weak strong uniqueness. But for quadratic it was proved, but in the general case, it's probably more difficult. So essentially, that's it. Thank you.